Okay, let's get started. Well, I guess the rain is probably giving people some trouble commuting, but we have to, start. Um, so today we're going to continue with our discussion on the Tannery liquid-liquid system. Okay, so just a brief introduction. So we've sent this slide on Monday. So the reason we want to talk about Tannery liquid-liquid system is that because this liquid-liquid extraction technique is a very commonly used separation process in not only the chemical industry, but also in the mineral, metallurgical, and the food industry. Here, the idea is that if you have a feed in which your solute B that's of interest is dissolved in a carrier A, then you can use a solvent C to contact your feed in this kind of like a separation unit. Then because, in this case, ideally A and C, they are two immiscible liquids. But practically most of the time they are only, you can never achieve, complete immiscible. So typically they are partially immiscible. Because the solubility of the solute B is different in the component A and C, then we will be able to transfer solute B from your carrier A into your solvent C, and then we'll have two exciting streams. One is called extract, that is rich in B, right, with the solvent C, and then the other is called raffinate, in which we have the solute B and we have some leftover solute B in the component A. Right? This is kind of it's how it works. So this liquid-liquid extraction is super popular in a lot of practices. For example, it's being widely used in the extraction of metals in hydrometallurgy, right? So Utah is a state full of minerals, and not far away from Salt Lake, we have the biggest copper mine in the city of Coppertown. And the way you do copper extraction is you mine a copper ore, then you dissolve it with an acid, right? And acid will basically dissolve the copper ore, typically copper oxide, with other copper compound. Then copper will get into the liquid stream as a solid in the form of iron. Now you can use the organic solvent to extract the copper from that water stream, right? Then you can concentrate the copper in your extract. You can also extract organic compounds in chemical industry. For example, you can use ether to extract acetic acid from water. Or in the process of making biodiesel, you are trying, in the process of making biodiesel, you are reacting a methanol ethanol with some vegetables or plants, right? Then you will produce some organic compounds plus water. Then you can use some organic compound to extract the formed biodiesel from this mixture. That's there some applications. In a lab scale, if you go to a chemical lab, and this solvent extraction process is also commonly used with using this device, right? This is called a separatory funnel, in which, for example, if you synthesize some chemical which is soluble in water, now you want to extract it, right? So here you first fill this funnel with this water solution of your solid. Then you can add a immiscible solvent. Typically, this is an organic solvent, and that's lighter than water. The given time, this organic solvent will basically, the solute B will transfer from your liquid water phase into your, organic phase. Then you can use this to separate it, right? And this is a separatory funnel looks like in a chemical lab, right? You have this pear-shaped glass. There's a funnel down here. There's also ways you can do this continuously by using a column. But in this case, these columns are kind of mini columns compared to the columns used in the industry. So basically, these columns are a glass column, then with kind of 4 entrances, 2 here and 2 here, and inside of them there's some metal structure just to enhance the mixing between the 2 liquids. So what you do here is you feed your lighter liquid, feed here, here. Then you feed your solvent, like your heavier solvent here, your heavier phase, right? Could be the solvent, could be the feed here. Then the heavier phase will drip down, and while the lighter phase will, go up. Then eventually you will have a lighter stream coming out, right? And the heavier stream coming out here. Okay. In industry, there are different equipment to do this. One equipment is called a mixer settler, where you have the lighter phase and heavier phase entering this unit, which is called a mixer, right? You are agitating this mixture to ensure they are well mixed. Then they will enter the second kind of part of this operation that's called a settler, in this settler, because we have 2 immiscible liquids and they have different density, and because of gravity, the heavier phase will settle while the lighter phase will float. Then you can just separate them, right, with 2 exits here. There's also a way to use centrifugal force to facilitate the separation, right? Because gravity sometimes can be slow. If you want to do this quickly, you can use this centrifuge contractor. The structure of such a centrifuge contractor looks like this. You have the axis here. This is a rotor, and you have your lighter phase and heavier phase feeding from the side. Then they will enter this mixing chamber here. Okay. Then once we start to rotate this rotor, then these 2 phases will contact each other and mix in this green region, and eventually the lighter phase, which is the yellow here, because they are lighter, so they don't experience as much centrifuge force compared to the heavier phase. They will stay close to the axis, whereas the heavier phase will be kind of spin far away from the axis. Then you can extract them. That's another instrument you use in industry. With centrifuge, then you can really do the mixing and the separation very quickly. Okay. So then we talked briefly in Monday's lecture that in the ideal case, we have that's a carrier that's insoluble in solvent C. In this case, when we contact the solvent with the feed, we will end up with 2 streams. The extract, right, that is enriched with solute B, but there's no A because A is insoluble in C, and we'll have a raffinate that is depleted in B, right? In this case, because both of the extract and raffinate streams, they are binary mixture, so that just makes it easier for us to use simple mass balance to do the analysis. Whereas in the other case, if A is partially soluble in solvent C, then in the 2 exit streams, we will have, the extract, we will have some carrier A dissolved in C. In the raffinate, we will have some solvent C dissolved in A. So we'll end up with 2 ternary mixture. And in this case, we have to use the ternary phase diagram to analyze it. Okay. And we talk about this briefly. So basically, for this case, for case 1, we can write down the mass balance equations for carrier A, right? That's present in the feed and in the raffinate, and solvent C that's present in the solvent stream and the exiting extract stream. Then we have solute B present in the feed and extract and raffinate, right? So we just write down the mass balance equation by multiplying their mole fractions with their corresponding flow rate, molar flow rate. Then we can use AC balance to eliminate R and E in the B balance, right? Here is just like we rearrange this term to get E as S divided by XC, and replace this E with that. And similarly, we can replace R here with the R here, right? You know, by dividing XA to the left, right? Then plug in, so you have this. Then to further simplify this equation, we have to make some kind of definitions here. Basically, we define, two concepts. One is the so-called molar ratio of B to other component. We denote it as capital XB. That is just the ratio of molar fraction of B in the extract over the molar fraction of C in the extract, right? Because in this case, in the extract, we have only two species, B and C. So then the molar ratio of B to the other component refers to the molar fraction of B to the molar fraction of C. Similarly, we can write down the molar ratio of B in the raffinate to be the ratio of molar fraction of B with respect to the molar fraction of A in the raffinate, right? Because in the raffinate, we have only A and B present. Okay. So then now you can just plug in these definitions. Here we have XB over XA in the raffinate, right? That's just this one, right? So we just replace this ratio with capital XBR. So here we have XB over XC in the extract, right? And that's just the definition. This one, we can replace this with capital XBE. So here we can replace F with FA divided by XA, right? So here we define the flow rate of A in the fade is the mole fraction of A multiplied by the total flow rate, right? So and if you divide XA to the left, you have F equals FA divided by XAF, right? Just plug in there. Then you have XBF divided by XAF, and that's the definition of capital XBF, right? So now we have this simplified equation. Let's see what we can do with it. Now let's make some further definition here. If we define a K value, K prime, this is like a D means distribution, right? Distribution will be factor prime is the molar ratio of B in the extract, right? Compared to the molar ratio of B in the raffinate. And by definition, this equals XB, lowercase xb over lowercase xa in the extract, right? And this corresponds to the lowercase xb divided by lowercase xa in the raffinate, right? Then xb e over xbr, that's the definition for distribution coefficient, right? Because b is the mole fraction in the extract, and r, well, this is a mole fraction of b in the extract, and this is a mole fraction of B in the raffinate. Okay, so that's to satisfy the definition of K value for a liquid stream, right? We talked about this briefly in the thermodynamic review. This is kind of equivalent of the K value for the vapor liquid examples we talked about in the flash calculation, right? So so basically that's kind of the thermodynamic driving force for us to separate, to transfer solid B from phase from A to C, right? That's similar to the flash calculation, in which we leverage the key value difference between different species, right? Between a liquid and vapor phase, right? If we have a liquid stream, we can partially vaporize that liquid fate. Then because each component have different key values, they will have different mole fractions in the vapor phase and compared to the liquid phase. That's how you separate it. So in this case, the solid B will have different solubility or mole fraction in the extract and the raffinate, right? So K value here is not 1. That's how we can, achieve the separation Then back here, XC in the extract is just, and we can take it to the, to here, that's 1 minus XB in the extract, right? Because there's only 2 species in the extract, their mole fraction should sum up to 1. Similarly, XA is 1 minus XB, right? Because in the raffinate, there are only A and B. Okay, we do this. Now, we can, with this definition, now we can just divide this equation by capital XB in the raffinate multiplied by FA. Then we can get this, right? So this is a little bit not very straightforward, so we can write it down. So if we divide this XB FA, or we divide this equation by this term, then this will become 1. Right? And this term will become, so we have XBE divided by XBR, right? That's just the definition of this. That will give us K prime D B. Then we have S divided by FA. Okay. Then on the left-hand side, FA, they cancel with each other. So we have X BF divided by X B. Okay. So that equals this term. Okay. Now, in order to get this equation, we just need to take the inverse of this whole equation, right? Then on the left-hand side, we can flip R, XBR to above the line, and we can flip the XBF below the line. And here we have this rise to -1 power, right? Okay. So now let's look at what this physical meaning of this equation. So here, XBR over XBF is kind of like the molar ratio of B in the extract compared to the molar ratio of B in the feed, right? So in the separation process, ideally we would like to have as little solute B in the raffinate as possible, right? Compared to the feed, right? So that's kind of the goal to achieve an ideal separation. Now let's look at these parameters, right? K prime, as we just discussed, it's basically the distribution coefficient, and the higher the K value is, then basically the higher and the smaller this term is, then the smaller this is, right? The higher the solvent flow rate is, and the lower FA is, then basically we have a greater value of this term. Then we have a smaller value of this value. If you rise to -1 power, then we have a small value of this ratio. That means we have a better separation factor. So that's why this factor is defined as extraction factor, and the larger the greater of this term is, the better separation we can achieve. Okay. And in your textbook, this extraction factor is denoted as EB, right? Extraction E refers to extraction, B is component B. Then we can basically rewrite this equation to get EB to be this. Now let's look at one example. This is one example from your textbook. Let's say we have in a chemical reaction, we have produced acetic acid, right? But it's mixed with water at a mole weight fraction of 8%, right? Now we are trying to extract the acetic acid from this water acetic acid mixture using this organic solvent, methyl isobutyl ketone, right? That's our solvent C. And we don't do this using vaporization, because that would mean we have to vaporize a lot of water, which is not very energy efficient. So we're using this liquid extraction process. Now, if we want to minimize raffinate, right? In practical applications, you cannot minimize it to zeros, right? You have to define a threshold. So in this case, we minimize the raffinate to 1%, 1 weight percent of acetic acid, right? Now, how much solvent do we need to achieve this separation, to achieve this goal? Now, let's just compare what the problem statement has provided us with the equation we just derived, right? So now we know that the kind of the weight fraction of acetic acid in the feed, right? So we know this term. And we also know the flow rate of the feed, so we know this one, right? And we know the separation outcome we want to achieve, that's 1% acetic acid, so we know this, right? And now we're asked to solve for S, right? Just solvent flow rate. So the only missing puzzle is just key value, right? So which we can basically, if we assume, first we assume water and solvent are immiscible, right? So that that's why we can use this equation. Then we can find the key value of acetic acid in this solvent from Paris Chemical Engineers Handbook, which is 0.657. Now, because we know the key, what we really need is K prime. That's dependent on both key value and this ratio. But because here, this is 1%, right? This is maybe a very small quantity. We can make an assumption that, you know, these two values are equal, right? That will simplify the calculation. Now we can do the rest is just math. So first we compute the flow rate of A in the feed, right? By the mole fraction of A, which is 92%, right? That's 1 minus 8%, multiplied by the total flow rate to give us this number. We can compute the molar ratio of B in the feed. That is the molar flow rate of B, right? Divided by the molar flow rate of water. Okay, we can compute. So that gives us this value. Then we can compute this value, which is molar ratio of B in the raffinate, which is 1%, right? Divided by 1 minus 1%. Right? That gives us this value. We can calculate the extraction factor, which by definition you just plug in these two numbers, right? Plugging these two numbers here, you get 7.61. Then you can calculate the solvent flow rate, right? By using this equation here. Just rearrange this equation and just take this and this to the left. Plug in the numbers, you get this flow rate, right? So we need a solvent flow rate of over 100,000 kilogram per hour in order to achieve a separation that has a raffinate with that raffinate that contains only 1% of acetic acid. Is this a good process? So one way we can look at it is if you compare this, how much solvent you need to how much feed you have, right? Just look at the digits, right? You will see this is more than 10 times more than the feed, right? That's really not a very efficient way of separation. So for this particular case, single stage process is not ideal. So we probably need to use a multi-stage process, or we have to find out another solvent with a much larger distribution coefficient than the isobutyl ketone, so that we can improve this process. Okay. Now let's move on to case 2. So case 1 is pretty simple, right? You just plug in the numbers and you can analyze it. Case 2 is more complicated because in this case, A is partially soluble in C, so we have then both extract and raffinate are ternary phases, that contains both A and B and C, right? To solve this problem, we have to know the phase equilibrium. So next, I'm just going to spend some time just to briefly recap a ternary phase diagram, how to read it, right? So I think you have learned this in thermal. So I'll do it briefly. The way we can look at it is in this triangle, this equilateral triangle, each corner represents a pure phase, right? So here we have pure phase A here. Then the edge that's on the opposite of the, A represents 0% of A, right? There's no A there. Then this triangle is like three pyramids overlapping with each other. And now if we want to read the composition of A, then we're reading this A pyramid with edge here and at apex here. And at apex, we have pure A, so the ratio is 100%. At the edge, the bottom edge, we have 0%. Then in between, we can read the corresponding ratio of A by just looking at the lines that's parallel to the edge, right? We call them as stairs. For example, at this line, we have basically 10% A, right? At this line, we have 20% A. Right. Now, if we add the second component B, right, now we are reading another pyramid with apex at this point with the edge here. So then this line represents 0% of B, and this point represents 100% of B. And any lines in between that's parallel to this edge line represents a fraction that's in between 0 and 100%, right? For example, this line represents 90% of B, right? And this line represents 10% of B. Similarly, you can do the same with C, where you read the lines, right, in parallel with this edge. That's how you read it. Okay. So this Taylor phase diagram is obtained at a constant pressure and temperature. So the question, what's composition at this point indicated here? Any?
60 of B and 40 of B. No, it's 40, 40.
So yeah, so if you look at this, right, we can read A first, right? Then we read this, labels here and read this line, that's 40% A, right? And then B here, we read all the lines parallel to this, then we go here, that's 40% B, right? And C here, that's gonna be 20% C. Okay. Now let's look at the example for the separation. So here we have a basically a fate with water and ethylene glycol, right? They are miscible, completely miscible. And now we want to extract ethylene glycol from water by using the solvent C, furfural, right? Furfural is also completely miscible with ethylene glycol, but it's only partially miscible with water, right? How do we do this? First, let's look at this phase diagram with two miscible pairs and one immiscible pair. We have to learn to read this diagram. Key concepts. What are these points? What are the apex? Right? The point A, B, C. We just talked about. That's pure phase A, B, C. Each edge line represents a mixture between the two phases, right? For example, this edge line represents the mixture of furfural with ethylene glycol. Okay. Any point in the triangle, right, that refers to a composition has both A and B and C, right? But depending if this point is outside this envelope, it can have two meanings. If it's outside this envelope, then this, for example, a point here would represent a homogeneous mixture, contains ABC. There's no phase separation, only one phase. However, if you look at any point within this envelope, we call it miscibility boundary, then it will phase separate into two immiscible coexisting phases. Okay, so point D and G on this line just represents the immiscible boundary of furfural and water, right? So in the range from point C to D, you have water that's completely dissolved in furfural with one phase. In this range G to A, you have furfural completely dissolved in water. However, if you are ending up in the region between point D and G, so you have a mixture of two phases with composition at this point D and composition at this point G. Okay. And then line DPRG, right? DEPRG just gives you this so-called miscibility boundary. Outside this boundary, you have a homogeneous phase, and inside this boundary, you're gonna have two phase coexist. Okay. Then point B is plate point. Before we talk about plate point, let's talk about EMR. So now we have a line EMR. This is called tie line. Tie line means if you have a composition sitting on this line, anywhere on this line, then the composition will phase separate into two phases, right? How do we know the composition of these two constituting phases? And we have to look at, how the tie line basically cross the miscibility boundary. In this particular case, if you have composition sitting on this tie line, then this composition will be made of will be made of two phases. One phase sitting with a composition at E, one phase at a composition of R, right? And there are many tie lines in this miscibility boundary. I mean, obviously, the lowest tie line is DG, right? And as you increase the concentration of ethylene glycol, the tie line will go up, and eventually it will it will be shorter and shorter, and then converge to a point here. That's called the plate point. Okay. Then now if we draw let's say we draw a random line connecting water with any composition here in this point, what does this line mean? So basically, in this Terry phase diagram, if you draw any line, right? Physically, that means draw any line connecting, for example, one point to the other point. That means you are trying to mix in the composition of two endpoints, right? In this case, you are trying to mix water with a phase, right, that contains 50% of furfural and 50% of ethylene glycol, which turns out to be a homogeneous phase, right? Because they are immiscible with each other. Okay, so now you are trying to mixing them, and depending on which point you are sitting at, right? It can be you can make a homogeneous solution, right? If it's between HI and JA, and it can also be two phase coexist if it's IJ, right? Because in this case, the composition is going to enter this miscibility boundary. Okay. Now, for our example, we are using furfural to extract ethylene glycol from water, right? Then we will end up with a phase that's furfural rich, right? That's going to be the extract, right? Because we're using furfural as a solvent. We'll have another phase exiting separation unit with water-rich phase. That's a raffinate. Yes.
What if you draw the line, but it's like not inside of the envelope? It's just like above in the B-rich phase.
Yeah. So you were saying if you draw a line, for example, connecting the 0.7 with 0.4.
Yeah.
So in that case, you are mixing a ethylene glycol furfural mixture with 70% of ethylene glycol with a ethylene glycol water mixture with 40% of water. Okay, then because if you draw this line will be outside its miscibility boundary. That means any points, however you mix it, however the ratio you change to any composition, you will end up with a homogeneous solution with no phase separation. Right? So another way to understand is in this phase diagram, any point represents a particular composition with ABC specified, and any line that will give you 1 degree of freedom that represents a series of composition in which you have to specify. You only have two constraints. Okay? Yes,
But if you, like, in that example with that red line, you mix that, does it not, are you saying that it doesn't depend on how much of both the solutions you get, the two, or you put in and mix together, the two, like, two phases are going to be with, like, the compositions on the two dots on the edges of the envelope?
can you rephrase your question one more time?
Like, will they always have those compositions?
You mean IJ?
Mhm.
Yes. At this particular pressure and temperature, given this phase diagram, if you mix them, if the overall composition is here, right, then you're gonna have a homogeneous solution. Right? However, if your overall composition is here, then you don't have a homogeneous solution. You will have a mixture of I and J phase separate. Yeah. So now let's look at one example. Let's see if we have a fate that contains 45% weight of glycol and 55% of water. And now we're contacting this water solution with twice the weight of the pure furfural, right? How much extract and raffinate we can obtain if we have 100 grams of aqueous feed, right? I mean, to answer this question, basically 2 steps. First, you have to basically locate the composition of the feed and the composition of your extract and raffinate on the phase diagram. The second, you can solve this problem, mass balance problem, using graphical method, using the inverse leveler arm rule. So now here we start from a mixture of glycol and water, right? And we have to look at this edge line because we have 45% glycol, right? And that will be, so we have 55% of water, right? Pure water is here and 55% is there. So that's our kind of starting point. That's our feed composition. Meanwhile, we're contacting with furfural, pure furfural, that's sitting here, right? Now, as we just discussed, now you're mixing this with that, and depending on the ratio of the two, the overall composition can be anywhere on this line. Then we need to find out exactly in this case where that overall composition will be. Right? And here, this is where you can use the inverse lever arm rule. So that now, because you have this part, this fate is contacted with twice its weight in the pure furfural. That means this fate, it will only consist 1/3 of the total weight after mixing, right? Then by using the inverse leveler rule, we kind of have to find a point on this line that sit at basically 1/3 of the position from the furfural, right? Because it's inverse leveler arm rule. So it should be the water glycol mixture is 1/3 of the mixture. Then when you find this point needs to sit at a location that's 1/3 distant from the other component, right? That's inverse leveler rule. That's how we can find this point. So you need to be able to use this. And if I give you a figure, and then you need to be able to use a ruler to find the timeline, find the composition, then read the end composition. Okay. Then if you read the point, then this end composition is sitting at this timeline, right? E and R. Which means now if after sufficient mixing, we will end up with 2 phases. One has a composition at point E, one at R, right? And we can read this figure. And for the extract E, we can read A period first, right? We read all the lines here. That's about 4%. Then for B, we can read this B pyramid, right? We can read all the lines here, and that's about 9%. Then we can either read C or we can calculate C by 1 minus A and B. Okay. Similarly, you can read raffinate. Now we can extract, we can compute how much extract and raffinate we have. For 100 gram of feed, we have 200 gram of solvent. That make it total 300 grams. And then for the extract, again, now we have to use the inverse lever rule, right? Amount of the extract will depend on the length of MR compared to ER, right? So basically, amount of E is basically this M, amount of M multiplied by the ratio of MR, like MR divided by ER. Okay, that's how you use inverse lever on it. Right. Amount of raffinate R is amount of total amount M multiplied by, right, that's amount of R here, is the length of this line segment divided by this whole ER line segment, right, and then multiplied by total weight. Okay, now let's look at another example. Before we look at another example, I want to introduce, this is another way of, another type of ternary phase diagram compared to the equilateral phase diagram. This is a right rectangular phase diagram. And basically here, you have the mass fraction of C as the x-axis and mass fraction of B as a y-axis. And now in order to read the mass fraction of C, you read all the vertical lines, right? And in order to read the mass fraction of B, you read all the horizontal lines. Then for A, you don't read it directly from this figure. You just compute it by 1 minus B and XB and XC. Okay. Now let's look at an example. So, in the previous example, we are trying to use a ketone to extract acetic acid from water. In this example, we are using ether as a solvent to extract acetic acid A from water B, right? No, in this example, this is an example from another textbook. So they use A for the solute and B as a carrier. So it's slightly different. Note that. So this is the phase diagram, rectangular phase diagram. So we have the mass fraction of A and mass fraction of C, right? Mass fraction of A, that's your solute. This is the mass fraction of C, that's your solvent. So in the extract, we use YA, right? In the raffinate, we use XA. So that's just different. Just like previously, we use XA for the liquid stream and composition, and we use YA for the vapor phase composition. Similarly, we have, in this case, we have also a miscibility boundary that's given by this line. Outside this miscibility boundary, you have one phase region, and inside you have two phase region, right? And because ether is the solvent here, so the region near on this side is the extract, and water is a carrier. So region down here is the raffinate. Okay. So then if we have a overall composition of H, then what would be the extract and raffinate composition by reading this figure? So first you find a tie line that goes through point H, right? In this case, it's G line GHI. Then you can read the composition of G and composition of I, right? And there's another way to plot the ternary phase diagram is this bottom figure, where we plot the ether layer. This is like the so the A is the solid, the solute composition in the extract versus the solute composition in the raffinate. Okay, then this IG point just corresponds to this point, right? Why is that? So this is a little bit, not very straightforward, but let's do this. So we know I is a raffinate. And then by reading the X coordinate on this figure, we can get the, the mass fraction of the solute A in the raffinate, right? That gives us the X coordinate in this figure, right? Because in this figure, we have the X coordinate is just the, the fraction, the composition of A in the raffinate, right? That gives us the X coordinate, right? So just draw a vertical line. Note these two axes have the same range and the same physical meaning. So you can just, so they have the same X coordinate. Then this point gives you the composition of your raffinate, of your extract, right? So again, the X axis here gives you the mole fraction of solute in the extract. And if you draw a vertical line, this vertical line will basically intercept with a 45-degree line here. And we know in a 45-degree line refers to YA equals XA, right? So that line intercept with a 45-degree line, then the y-axis here. So then the x-axis here just give you the y-axis. Well, that gives you the composition of the A in the extract layer, right? So that's how these 2 points GI can be summarized into 1 point on this figure, right? That's kind of the convenience of it. Now let's look at another example. Let's say we have an original mixture of 100 kilogram, and that contains 30 kilogram of isopropyl ether and 10, that's our solvent, 10 kilogram of acetic acid and 10 kilogram of water. They are equilibrated and the equilibrium phase separate. What are the composition of the 2 equilibrium phase? Right. First thing we do is, let's first just compute the composition of the feed, right? That's X, A, B, C, 10%, 60%, 30%, right? Just very simply. Then we can locate, that gives us this point, okay? Then we can locate the extract, that's basically this point, right? And if you read that point, that gives us a composition of 4% A and 94% of C, then B you can compute by 1 minus A and B, right? Similarly, you can find the raffinate composition by this point. Okay.
Shouldn't that be I instead of G on the raffinate? This is raffinate G.
Oh, sorry, there's a typo here. So that should be extract should be G and raffinate should be I. That's a typo. Okay. Okay. So that's it for the ternary liquid equilibrium. So for next lecture, we're going to start to talk about absorption and desorption.